You press the power button. The cooling fans spin up with a sudden burst of energy, and then an immediate click. Dead stillness. This failure occurs in the pre-OS environment. At this stage, your operating system hasn't loaded, meaning your standard software diagnostic tools are completely useless. To figure out what went wrong, we need to look at the strict chronological timeline of the boot process: power, post, UEFI firmware, security, and finally, the OS. First, raw electricity must successfully trigger a basic hardware self-test, verifying the critical physical components. If that passes, the system hands control to the motherboard's firmware, identifying available storage and system configuration. Modern architecture introduces a strict security check here. Hardware-level validation must authenticate the system before the operating system is allowed to take over. Hardware troubleshooting relies on the systematic isolation of variables along this specific chronological path. Guessing has no place here. Without this timeline, a technician is flying blind. By tracking the exact sequence of handoffs, you isolate the specific component causing the failure. Let's start at the absolute beginning of the sequence. Before diving into complex logic boards, we must verify the physical baseline. That means checking the wall outlet, inspecting the power supply switch, and verifying the power supply unit itself is outputting the correct voltage. When the CPU receives a clean power good signal, it initiates the power on self-test, rapidly scanning the RAM and graphics processing unit. If post fails, the primary symptom is distinct. The system has physical power, but outputs a dead black screen with no manufacturer logo and no diagnostic beeps. Your immediate physical isolation step here is to reseat the components. An improperly seated stick of RAM or a loose GPU are primary culprits for a no-post scenario. If reseating fails, the next escalation is clearing the CMOS. This resets the motherboard's firmware settings back to their factory defaults. The final physical test for post failures is stripping the system down to minimal hardware, just the CPU, a single stick of RAM, and onboard video. A dead black screen is rarely a total mystery. It indicates a verifiable failure of power delivery or basic physical component seating. Once post succeeds, control passes to the firmware. For decades, this meant the Basic Input-Output System, or BIOS. Today, it means the Unified Extensible Firmware Interface, or UEFI. This chart directly compares the technical capabilities of legacy BIOS and modern UEFI. Under the BIOS column, notice the strict capacity ceiling. It relies on the master boot record formatting, limiting you to drives of 2 terabytes and a maximum of 4 primary partitions. Over in the UEFI column, that ceiling disappears. UEFI utilizes the GUID partition table standard, supporting massive disks and over 100 distinct partitions. This visual highlights the interface evolution, contrasting the text-heavy BIOS on top with the graphical UEFI dashboard below. While legacy BIOS relies on basic keyboard navigation, operating in a 16-bit environment, UEFI leverages full 64-bit CPU operation to support complex graphical interfaces and mouse control. The industry adopted UEFI as a necessary architectural upgrade because modern massive storage drives literally broke the physical limitations of 16-bit BIOS. Modern systems boot incredibly fast. As a result, it is common to completely miss the traditional F2 or delete key prompt needed to enter the firmware setup. This graphic shows the software workaround to access UEFI if the OS is running. You navigate through Windows Advanced Startup options. Alternatively, force the advanced boot menu from the command line using the shutdown command with specific restart parameters. Once inside UEFI, you troubleshoot errors like bootable device not found. This mockup illustrates the boot priority order, listing the Windows Boot Manager and connected storage. Look at the sections below. If a drive fails to appear in this device list entirely, you must step back and isolate physical connection issues, like SATA cables or NVMe seating, before assuming the drive is completely dead. Beyond storage, UEFI manages environmental stability. This slide illustrates the hardware monitoring capabilities, displaying real-time CPU temperatures and fan RPMs. Technicians directly manipulate cooling behavior here, selecting preset profiles or building custom fan curves tied to specific temperature thresholds. Modern UEFI operates as a complete diagnostic dashboard. It allows you to stabilize hardware parameters before the operating system is even a factor. We reach the final layer of the pre-OS environment. UEFI does not simply hand over control to the storage drive. It actively polices what is allowed to execute. This graphic maps the purpose of Secure Boot, illustrating the verified trust chain flowing from the firmware to the bootloader, through the drivers, and into the OS. The mechanism relies on cryptographic digital signatures. The firmware checks the OS bootloader signature. If the code has been altered by a rootkit or malware, the signature is invalid and the boot is halted immediately. This brings us to the physical hardware that manages these cryptographic keys, the Trusted Platform Module, detailed in this slide. The TPM acts as a secure vault. It provides hardware-based security by storing digital certificates, and it enables drive encryption features like BitLocker. As noted at the bottom, this hardware is a strict installation mandate for modern operating systems like Windows 11. Because modern PCs mandate authentication before booting, a security failure, like a TPM mismatch, will actively mimic a hardware failure. This trust chain serves as a critical troubleshooting node. Let's bring back our chronological timeline to synthesize this diagnostic model. If you get a black screen with no beeps, the system failed at the very beginning, at the power or post stage. A bootable device not found error means the failure lives in the UEFI storage configuration, or it's a physical drive connection issue. A secure boot violation, or a BitLocker lockout, indicates a failure right at the TPM security validation node. And if the system displays a blue screen of death, the hardware handed off successfully. Your investigation must now shift to OS drivers or software faults. Memorizing individual error codes is inefficient. Understanding the exact architectural flow of data is what defines a professional. By mastering this pre-OS timeline, you replace trial and error guessing with targeted, definitive diagnostics.